Hello everyone. In this video, we're going to continue talking about association between two quantitative variables. So in the last video, we talked about how we can make a scatter plot to look at the data, and then we can describe the direction, the strength, and the shape of that graph. Okay, and so we went in the last part of that video to talk about the correlation coefficient, which was a special number that describes how strong the association is if we have a linear relationship between the two variables. So if the data was linear, then we could report that correlation coefficient. Okay, and I will show you how to make the correlation coefficient in another video. Okay, if you haven't watched that video already, there will be one up. All right, so when there are, in addition to the correlation coefficient, which describes the strength of a linear relationship, we can do something extra when we have linear data. Okay, so we can do more than just report the correlation. We can create what I'm going to call a model that describes the relationship between the two variables. Okay, so we can do more than say that there is a linear relationship, it's strong, it has a correlation of 0.7. That does tell us something about the association, but it would be better if we could actually model that relationship. And so what I mean by model is that we're going to create a line of best fit. Okay, so that's what we're going to do. You've probably heard of that before. You've probably done that before. Creating a line of best fit is something that you do in high school. We're going to talk about it here, but under different circumstances than you've probably seen before. So we're going to create a line that fits the data. And so why would we do that? We would do that because we can then, what I said before, is describe the relationship between the two variables. So if I could, for instance, if I looked at heights and weights, okay, although I know that that's not a linear relationship, I'm going to assume it for this example, okay. If I believe that height and weight were linearly associated, okay, as your height goes up, your weight goes up as well, okay, great. I can say it's linear, there's a strong association, the correlation is 0.7, but if I can go further and say that for every inch of height that you gain, you will gain about 5 pounds. That says something more than just that there is a relationship there. It describes that relationship almost exactly. Okay, so that's what I mean by a model there, and an actual equation that we're going to use is y hat equals a plus bx. So what you're used to in any math course that you've taken, okay, on algebra, so probably algebra 1 that you took in high school, is the line y equals mx plus b, okay, where m was the slope and b was the y-intercept. I'm going to change it around slightly, okay. A is the y-intercept and b is the slope here. Say, but don't get too weirded out. I'm sure you can make the change. And then the other weird thing that you'll see here that you probably won't see elsewhere is y with a hat over it, okay, or y with a little caret on top. I'm going to call that y hat, okay, and that means something special in statistics, okay. Anything with a hat on it means that it was predicted, Okay, and we'll talk a little bit about what that means later on in the slides. But anything that's predicted gets a y over it. So we're going to use the line a plus bx to predict values of y. All right. So the regression line, so we're going to call this linear regression. Okay. Before you called it line of best fit, we are calling it linear regression. It means the same thing, okay, for our purposes in this course. And the line y hat equals a plus bx is often called the regression line. It also is called the prediction equation, okay, because it predicts the values of y based on the values of x. So that's just what I was talking about before. All right. So here's an example. I've plotted city miles per gallon versus highway miles per gallon. And so as you would guess, those two are highly correlated. It's very unlikely to see a car that gets 8 miles per gallon city, but yet somehow magically 40 highway miles per gallon. Okay, so you'll see that they are linearly associated. So I usually ask the question, does the relationship look linear? And you would say yes. Okay, there is a linear relationship between the two. So then I can fit a line to that data. Okay, so we fit a line using software, and I'll show you how to do that. So we fit a line, great. And then we get an equation. Y hat equals 1.337x plus 0.892. Great. Okay, so we have the equation of the line. What do we do with it? Well, there's a couple things that we can do. The first thing that we can do, which is something that you've done before when you've looked at equations like this, is we can interpret the slope and the y-intercept of the prediction line. Okay, usually it doesn't mean so much in a math course, but in a statistics course like this, for the reasons that I've talked about before, these interpretations actually have a lot of meaning. All right, and so they're going to be ever so slightly different than what you've seen in a math course, and I want you to pay special attention to the difference, okay? Because it's a big difference. I'll talk about it a bunch, and I know you'll forget it because everyone always does, but I'm still going to talk about it a bunch. So here's the equation. Here is the interpretation of the slope of these kinds of lines. This is not for all lines that you'd see in a math course. This is for this line, okay, in the statistics course. The slope, and so if you think back, so before I talk about this, if you think back to your mathematical training, you'd interpret the slope as rise over run. Okay, rise over run for an, so you'd rise so much and then run so much. In statistics, we're never going to have fractions, and so we're always going to run by 1. So for an increase, a mathematical definition of slope is there's an increase of m in y for a 1 unit increase in x. As x increases by 1, y is going to increase by whatever the slope is. Okay. In this equation, I'm saying, or in this interpretation, I'm saying that the slope is the average change in y for a 1 unit change in x. And so there's only one word that has changed from the mathematical one to the statistical one, and that is average. Okay, that is average, but that's a big change. And it has implications. So if we go back to the height and weight example, okay, and if I made that line of best fit and maybe my slope was 2, okay, the interpretation of that slope is when I increase 1 pound in weight, the average increase in, height would be on the x-axis. For a 1 inch increase in height, I would expect a blank unit increase in weight. We know that all people are not the same. Okay, and so we have some people who are very short but weigh a lot. And then we have some people who are very tall and don't weigh a lot at all. And so we know that when you increase height by 1 for every person, the weight is not going to increase the same. This line is looking at the average increase. Okay, so if I had an increase of height, if I increased everyone on this earth's height by 1 inch and then saw how their weight changed in some magical world and then took the mean of all of those changes, that is what the slope is interpreted as. Okay, so I know that was a long answer or a long explanation. Hopefully that didn't make it more confusing than it already is. The takeaway here is use the word average. It is important. Okay, so for a 1 increase, so what does it mean in terms of this problem? It means for an increase of 1 city mile per gallon in a car, I expect a 1.337 increase in highway miles per gallon. Of course, every car is going to be different. Okay, but on average, it's going to increase by 1.337 miles per gallon. So hopefully that makes sense. All right, now the y-intercept. In a regular line that I'd make in a math course, the interpretation of the y-intercept would be the value for y when x is 0. And so it's the same thing here, except I add one word, which is average. So here it's the average value of y for an x value of 0. Now, oftentimes when I ask you these problems, I'm going to ask if the interpretation is appropriate or not. Okay? And what I mean by that is, does it have meaning in the world? In context of the problem, is it meaningful? For instance, for this line, it would say, for a car that gets 0 city miles per gallon, I expect that car to get around 0.892 highway miles per gallon. Does that make sense in context of the problem? Can I have a car that gets no city MPG, but gets highway MPG of 0.892? Certainly not. Okay, a car that gets 0 city miles per gallon is a car that's broken down, and it's still going to be broken down on the highway. So the interpretation of the y-intercept here doesn't make sense. And so I'm going to expect you to think about that. And then if it doesn't make sense, don't interpret it. Just say that it doesn't make sense. Okay, so oftentimes I will phrase it as, is it appropriate? If appropriate, interpret. So certainly if it's not appropriate, don't interpret. All right? Okay. And so one last thing that I'm going to talk about before we have our reading, before we will have the usual reading and your turn, is prediction using this line. Okay, so we can interpret the line and we can also predict values of y given values of x. Okay, so here again is our regression line. We can use it to predict new values of the response for a given x. Great. So for example, if I bring in a new car, okay, behind my magic black sheet, and I say that this car gets 22 city miles per gallon, what would you predict the highway MPG to be for this car? Okay, and so all that we have to do is substitute in 22 for x and then see what pops out of the equation, for lack of a better term. Okay, and so when I substitute in 22, I get out 30.31. And so, what does that mean? I predict that that car, which I can't see, would get 30.3 highway miles per gallon. Okay. Now you'll see in this class, you'll see that I didn't include the 1 after the 0.3. I don't care about rounding in this course. Okay. If I do, I will tell you how many decimals to round to. Okay. So in the homework problems online, they will tell you how many decimals to round to. Okay. I usually won't, and if I don't say it, I don't care how you round. Okay. Certainly, if it says 30.31, you should not round to 31. Okay. You should round to maybe at most 30.3. Okay. When in doubt, just give me the whole number. And what I mean by that is the number and the decimals. Okay. All right. So that's prediction. So there's no reading here. Certainly, if you go into the book, there will be parts that I talked about, but I included almost everything there in this video. So there's no really extra stuff that you'll gain by reading the book. Here's a your turn. All right, and so this is actually a fairly lengthy one, and it's going to include using StatCrunch. Okay, so I have some data here on honeybee waggle dances. Okay, which is a weird subject, but is actually kind of interesting when you think about it. Honeybees will do a waggle dance to communicate to the other bees about how far a possible new nesting site is. Okay, and so as the dance takes longer, the new site will be farther away. All right, and so I included a Wikipedia link if you want to read more about the waggle dance. Right, and I included the data set in our datasets folder on D2L so that you can download it and then load it into StatCrunch. And I ask you to do a bunch of tasks here. All right, some are going to require that you watch the video that will accompany this in showing you how to do regression type stuff in StatCrunch. Okay, so that's all for this video. I'll see you next time.